And this is going to be a mathematical demonstration of the Lagrange multiplier, and this is going to be the gradient, not the gradient, to the constraint, and set equal to 1, and that's going to be the function to maximize. So this is an animation. This curve here, as you can see, this is a constraint, and this level never changes. We're going to play with the level of this function f of xy. So you can see the level right now is a 0.32. Let me pause it. I was interrupted, but here, as you can see, none of these points, because this is the collection of all points, is level negative 0.32, and it does not intersect our constraint, so no points will hit that low level. But this one kind of overlapped too much, but let's just assume that it seems like now it touched it. So these are the collection of a points level negative 0.12, and then it finally intersected it, so we have a point on this ellipse that has that level negative 0.12. Right? So it seems like we can safely assume this roughly negative 0.12 seems like the minimum. Right, this I raised the level a little bit, so we have these 2 points there where it hits this level negative 0.82. So if you plug in these coordinates to f of xy that was shown earlier, the value is going to be positive 0.82. When I increase it a little bit further, we have these 2 points, and there's another 2 points, and these are the level 1.39. So we have these 4 points that is 1.39. When I raised it further, you're gonna kind of push it away to the different direction. So this is level 2.69. I'm gonna do more. All right, I'll pretend this looks good enough. So there's one point that's last point, kind of, that this point has this level 2.86. So there's a point 2.86. If I raise the level a little bit higher, like this, then it's going to be level 3.09. Then you can see there's no point that intersects this level, so no point is going to reach that high, 3.09. All right, that's the idea. When they intersect and with a tangency, then this gradient of this g and gradient of f must be pointing same or completely opposite direction. That gives you that Lagrange multiplier idea. This is three-dimensional, three variable version. So actually here's a g is this plane. So it's like, let me show you here, this plane set equal to something, maybe set equal to 1. And f is actually distance from this point, the 1, 0, 02, or negative 2, to some arbitrary position. So in this case, it's going to be like this. There's this plane, and we have a point on that plane. That's our constraint, so all the point must be there. So when you choose that point, and that's the level, and if you want to make it smaller, it seems like we have to choose these points. It seems like this level surface is getting smaller and smaller if we assume that's a smaller direction. And as you can see, about that point right there, it hits very inner level. So if you even make it smaller than this one, then there probably will not be any points that reach that level. So it's about there that it's going to assume the minimum. So that's the kind of three variable demonstration for a Lagrange multiplier for one constraint. Now this is a demonstration of a two constraint. All right, so we have one constraint that is given by a cubic surface, so that's outside here, and what you're inside is an ellipsoid that intersects. So if you have two constraints, it's going to be intersection of these two surfaces. Therefore, our constraint is not of these surfaces, but the intersection curve. So our constraint is not a surface, but it's a space curve. So I threw in this level surface. So this is fixed, this space curve, and these two surfaces are fixed. What is changing here is this level surface. That's why you see folds of many folds of this different levels. That's the level is changing. So what we have to look at is how this level surface is intersecting this space curve, not these surfaces. So this is a kind of the final picture. So as you can see, I chose the right level surface such that it intersects this level curve right there, and if I increase or decrease and it's just about to leave that intersection curve, this level surface will leave that point there. So I'm using this picture to demonstrate the relationship between this gradient vector. It's kind of a bit confusing here. So G1 is one of the probably ellipsoid gradient, and G2 is a cubic the gradient. And the tangent line, we've seen this type of problem in our exercise. This tangent line must be perpendicular because it's intersection perpendicular to G1 and G2. Okay, because this tangent line is the part of the tangent plane. So if you look at the G1, this thick black line is a part of the tangent plane, therefore it's perpendicular. If you look at G2, that is perpendicular to the tangent plane because this tangent line is part of the intersection, so it's a part of the tangent plane, so it's perpendicular to each other. Now if you think about this gradient of this level surface, that's the third one here, so that it's also perpendicular to this gradient, this tangent line, black tangent line right here. So therefore, all three gradients are perpendicular to this line, and this G1 and G2 forms a plane that is perpendicular to this tangent line of the space curve, the constraint curve. Therefore, the third gradient vector must be on the same plane, therefore it must be generated by G1 and G2. You know, if it is in the same plane, a linear combination of G1 and G2, stretching it and using the parallelogram law, you should be able to reach any vector in that plane. So therefore, this gradient vector of the level of the function to optimize is a linear combination of this gradient of G1 and gradient of G2. Okay? So as you can see, it's kind of in the same plane, they're all three vectors. So there's two Lagrange multipliers multiplied to lambda multiplied here, mu multiplied there, 2 is a vector. So lambda G1 plus mu G2 will be gradient of this function to optimize, f optimize. All right, looks cool. Thank you.